the dream becomes reality. Picture this. It's the year 2050, and somewhere on the dusty red surface of Mars, city lights are glowing in the darkness. Not from a tiny research station or a temporary camp, but from an actual city where thousands of people are living, working, and building a future. This isn't science fiction anymore. Companies like SpaceX are actively working on the technology, the rockets, and the systems to make this happen. But here's what most people don't understand. Building a city on Mars isn't just about getting there. It's about staying there forever. Let's talk about what makes a Mars settlement completely different from anything we've ever done in space. Think about the International Space Station or a future moon base. These are incredible achievements, but they have one massive advantage. Earth is close by. If something breaks, if supplies run low, if there's an emergency, help can arrive relatively quickly. The moon? You can get there in about 3 days. The International Space Station? That's just a few hours away, orbiting right above us. If you're living on the moon and you forget something important, no problem. The next supply ship can bring it within a week. Mars is a completely different game. With current rocket technology, Mars is roughly 8 months away. That's longer than a human pregnancy. That's 2/3 of a year floating through space just to reach the red planet. And even if we develop advanced nuclear propulsion systems, the best-case scenario still puts Mars about 45 days away. But here's where it gets really tricky. Mars and Earth don't stay at the same distance. They're both orbiting the Sun at different speeds, which means you can only launch missions to Mars during specific windows. These windows open up roughly once every 2 years. So imagine you're living on Mars and you desperately need something from Earth. Maybe it's critical equipment, medicine, or a spare part for life support. Well, even if Earth immediately prepares a shipment, you might wait 2 years for the launch window to open, then another 8 months for the ship to arrive. That's 2.5 years for one delivery. This is why Mars cannot depend on Earth. The people living there need to be completely self-sufficient. They need to produce their own food, generate their own power, create their own water, make their own oxygen, and manufacture their own fuel. Because eventually those supply ships from Earth are going to stop coming. Maybe Earth faces its own crisis. Maybe the cost becomes too high. Whatever the reason, the Martian colony needs to survive on its own. How many people do we actually need on Mars to make this work? Scientists estimate at least 1 million people for a truly self-sustaining civilization. Yes, 1 million. Why so many? Because a functioning civilization needs incredible diversity of skills. You need doctors and engineers, farmers and teachers, plumbers and electricians, scientists and construction workers, mechanics and miners. You need people who can fix a broken water pump at 3 in the morning and people who can perform emergency surgery. You need artists and psychologists for mental health, and mechanics who can repair vehicles in freezing temperatures. 1 million people gives you that diversity. It gives you redundancy, so if one specialist gets sick, others can step in. It gives you enough genetic diversity for healthy population growth, and it gives you enough hands to keep all essential systems running around the clock. This is a massive undertaking. Moving 1 million people to another planet is something humanity has never even come close to attempting. But that's the goal before we can truly call ourselves a multi-planetary species. So how do we start? Where do we even begin? We definitely don't begin with humans. That would be suicidal. The first inhabitants of Mars are going to be robots. Lots and lots of robots. Before a single human footprint appears in Martian dust, dozens or maybe hundreds of robotic workers will be crawling across the surface. And here's where things get interesting. Remember Optimus, that humanoid robot Tesla has been developing? The one that walks on 2 legs and can learn tasks through artificial intelligence? Yeah, that's not a coincidence. SpaceX and Tesla are sister companies with the same vision. Optimus is being designed specifically with Mars in mind. It's the perfect worker because it doesn't need oxygen, doesn't get cold, doesn't need food or water, and can work in radiation that would kill a human in hours. The timeline? Optimistically, this could happen as early as 2026. The plan is to send 5 Starship rockets to Mars, each carrying about 10 tons of cargo. And the primary goal of this first mission is simple: land at least one ship successfully without crashing. That's it. That's the whole objective. Why such a modest goal? Because SpaceX knows from experience that new technology fails a lot. They've blown up more rocket prototypes than most companies have ever built. But that's their strategy. Fail fast, learn quickly, improve, test until it breaks, figure out why, fix it, and try again. So they're sending 5 ships because they expect several to crash. But if even one lands successfully and deploys its cargo of Optimus robots onto the Martian surface, that's a huge victory. Those first robots won't have much to do initially. They'll explore, test the soil, check equipment, and wait. Wait for the next wave. 2 years later, the real work starts. This time it's not 5 ships. It's 20 Starship landers, each carrying 75 tons of cargo. This is where actual construction begins. Most of that cargo is equipment: solar panels, batteries, manufacturing equipment, mining tools, inflatable habitats, life support systems, water processors, chemical reactors, and thousands of other components needed to build a functioning colony. The Optimus robots will assemble and install all of this. But before we go further, we need to talk about location. You can't just land anywhere on Mars and hope for the best. SpaceX has identified their target: the Arcadia region, located just northeast of Olympus Mons, the tallest volcano in the entire solar system. This mountain is absolutely massive, standing about 72,000 feet tall. That's nearly 3 times the height of Mount Everest. But we're not building on the volcano. We're building nearby in Arcadia, and here's why. First, Arcadia is relatively flat. Flat ground makes construction easier, provides stable landing sites for rockets, and reduces the risk of equipment tipping over. Second, Arcadia is close to the Martian equator. This means slightly warmer temperatures, though still well below freezing, and more consistent sunlight for solar power. Third, and most important, Arcadia is believed to contain massive deposits of water ice just beneath the surface. Water is the single most valuable resource Mars has to offer. When the robots start unpacking cargo, they have 2 absolute priority projects. These machines need to be operational before anything else. Humans are roughly 60% water by weight. We need to drink it constantly. We need it for cooking, cleaning, maintaining hygiene. Water is life. But water is incredibly heavy. 1 gallon weighs about 8 pounds. A person needs about half a gallon per day just to stay hydrated. For an 8-month journey to Mars, that's 120 gallons per person, nearly 1,000 pounds of water for one person's drinking supply alone. Multiply that by dozens of people per ship, and you see the problem. The weight is enormous. This is why spacecraft recycle water obsessively. The International Space Station recycles about 93% of all water, including urine and sweat. But even with perfect recycling, there's a limit. Eventually, you need fresh water. That's where Martian water ice comes in. The robots build a processing facility that extracts ice from beneath the surface, melts it, purifies it, and makes it safe for drinking. This provides all the water the colony needs without depending on Earth. But water isn't just for drinking. Water is made of hydrogen and oxygen. 2 hydrogen atoms bonded to 1 oxygen atom, H2O. We can split water apart through electrolysis, running an electrical current through it to separate the elements. Oxygen is what humans breathe. So the same plant producing drinking water can also produce breathable air. 1 facility, 2 critical life support functions. But what about the hydrogen? That brings us to machine number 2. When the first humans arrive on Mars, they're going to want the option of going home. In the long term, Mars colonization might involve one-way tickets. But in the early days, you need to give people hope. Let them know that if things go wrong, they can return. Here's the problem. Rocket fuel is extremely heavy. Just getting enough fuel to travel to Mars and land safely takes up most of the rocket's capacity. There's nothing left for a return journey. So if humans want to come back to Earth, they need to refuel on Mars. They need to produce rocket fuel right there on the surface. SpaceX chose methane as fuel for Starship. Methane is easier to handle than pure hydrogen. It's 1 carbon atom for every 4 hydrogen atoms. Chemical formula CH4. That extra carbon helps stabilize the molecule and makes it safer to store. To make methane on Mars, we need hydrogen and carbon. We know where hydrogen comes from: water. Split water with electrolysis, capture the hydrogen, and you've got half your fuel. But where does carbon come from? Out of thin air. Literally. Mars has an atmosphere. It's incredibly thin, about 1% the density of Earth's atmosphere, but it exists. And that atmosphere is about 95% carbon dioxide, CO2. The fuel production plant includes a carbon capture system that sucks in Martian air, extracts carbon from carbon dioxide, and combines it with hydrogen to create methane. And here's a bonus. When you break apart CO2 to get carbon, you're left with extra oxygen, more breathable air for the colonists, completely free. To support these facilities, we need mining. The water ice is buried underground, so we need to dig. And conveniently, SpaceX has access to advanced tunneling technology through the Boring Company. A full-size tunnel boring machine is too big for early Mars missions, but the technology can be scaled down into a portable mining rig. Mining robots dig into the surface, extract ice-rich soil, and deliver it to the water plant. All the extra rock and soil that gets dug up isn't waste. It's valuable construction material. The mining waste can be processed into a substance similar to asphalt or concrete for roads, landing pads, and building foundations. By the end of Phase 2, roughly 4 years after the first landing, potentially around 2030, the Martian surface will have functioning water treatment, fuel manufacturing, active mining, process landing pads, and basic infrastructure ready for humans. The third wave lands. 100 Starship landers, each carrying 150 tons of cargo, and tucked among all that equipment are the first human beings to call Mars home. This is when everything changes. Robots don't need comfort, warmth, or complaint, but humans are fragile. We need specific temperatures, air pressure, and nutrition. We get tired, scared, and sick. Everything needs to work perfectly from the start. The first new construction project is a proper power plant. Robots have been running on battery power, recharging from small solar panels. That works for robots that can enter low-power sleep mode. But humans require constant power, 24 hours a day, 7 days a week, without interruption. Life support systems can't turn off. Oxygen generators run continuously. Water heaters stay on. Temperature control maintains livable environments. Lights work. Communication systems stay active. All of this requires serious electricity. Solar panels are the obvious choice. Mars gets plenty of sunlight, though it's dimmer than Earth since Mars is farther from the sun. But Mars has days and nights just like Earth. A Martian day, called a sol, is about 24 hours and 40 minutes. Every 12 hours, the sun sets and solar panels stop generating power. So we need batteries, big batteries. Tesla manufactures the Megapack, one of the largest battery storage systems in the world. A single Megapack can store enough energy to power a small town for several hours. A few Megapacks fit inside a Starship cargo hold. On Mars, they store energy during the day and release it at night, keeping all life support running continuously. Solar panels plus Megapacks create a reliable, renewable power grid. When colonists first arrive, they won't be homeless. The Starship landers themselves serve as temporary habitats. Each Starship is enormous, with multiple levels and plenty of interior space. They're pressurized with life support and can be connected together. But living in a Starship long-term isn't ideal. They're tall and narrow, requiring elevators or stairs every time you enter or exit. They're designed for transport, not comfort, so colonists need to build permanent homes. Most people imagine massive glass domes when they think of Mars colonies. It's a beautiful image, and eventually we might build something like that. But for the first settlement, way too complicated. The closest thing to a sci-fi Mars dome on Earth is probably Singapore's Changi Airport. The structure weighs about 3,500 tons. To transport that to Mars using Starship would require 35 separate rocket launches just for materials. Then you'd need massive construction equipment to assemble it. So we build ice domes instead. NASA's Langley Research Center is studying this concept. Ice is an incredible insulator. It keeps heat inside and cold outside. On Mars, ice has another critical benefit. It blocks radiation. One of the biggest dangers on Mars is solar radiation. The planet's atmosphere is so thin it provides almost no protection from the sun's harmful rays. Exposure causes serious health problems, including cancer. But water is one of the best radiation shields that exist. The atoms in water absorb and scatter radiation particles. This is why nuclear reactors on Earth are often surrounded by water pools. An ice dome gives you radiation protection, insulation, and shelter in one structure. Here's how it works. First, place an inflatable module on the ground, like a giant tough balloon that expands into a dome shape. Then build a mold around it. Finally, robotic workers fill the space between the inflatable interior and the mold with water, which freezes in the Martian cold. Once the ice is solid, remove the mold. You're left with a thick ice shell surrounding a pressurized living space. The ice is translucent, so natural sunlight filters through. This is hugely important for human psychology. Living under artificial lights 24/7 causes depression and disrupts sleep cycles. Ice domes are perfect for residential housing. For buildings needing more versatility, like laboratories or factories, we use inflatable modules covered with Martian concrete. Start with an inflatable structure from Earth. These can be manufactured in any shape, packed down small for transport, then inflate on Mars. Instead of ice, cover it with a shell made from Martian materials. All that rock and soil from mining operations can be turned into concrete. On Earth, concrete is rock aggregate mixed with a binding agent, usually cement. On Mars, we use Martian soil as aggregate. But what's the binder? Scientists at the University of Manchester developed astrocrete, or biocrete, using human bodily fluids as the binding agent, specifically urine. Before you get grossed out, remember, medieval builders mixed animal blood into mortar to make it stronger. This isn't entirely new. Every human produces about half a gallon of urine daily. We can extract drinking water from it, but waste product called urea gets left over. Urea mixed with Martian soil creates concrete stronger than what we use on Earth. Robots and humans mix batches of biocrete, spray or pour it over inflatable structures, and let it harden. The result is a sturdy, radiation-resistant building made from local materials. We've covered water, oxygen, power, and shelter. But there's one more essential need that's arguably the most difficult: food. You cannot bring enough food from Earth to feed a growing colony forever. Eventually, Mars needs to grow its own food. Farming is hard even on Earth, where we have rich soil, plenty of water, thick atmosphere, and plants perfectly adapted to our environment. Mars has none of those. The soil on Mars is toxic. It contains high levels of perchlorates, which include chlorine compounds. Chlorine kills bacteria and algae, which is why we put it in pools. It's terrible for growing plants. Perchlorates in Martian soil prevent almost anything from growing. So we have two options. Option 1. Transport soil from Earth, fill starships with dirt. But even a starship packed with nothing but soil doesn't give you much growing area. When you're feeding thousands or millions, you need vast agricultural fields. Option 2. Process Martian soil to remove perchlorates and add nutrients. Build an industrial facility that chemically treats soil, washing out toxic compounds and mixing in organic matter. Option 2 is more sustainable long-term. And once again, human waste comes to the rescue. While urine makes concrete, solid human waste can be composted for fertilizer. Every person becomes a producer of agricultural resources. Is it glamorous? No. Is it necessary? Absolutely. Once we process soil and fertilize it, we can grow crops, potatoes, wheat, vegetables, possibly fruit trees and controlled greenhouses. The colony will probably also include synthetic food production using bacteria or algae to create proteins and nutrients. It won't taste like a home-cooked meal from Earth, but it'll keep people alive and healthy. If we solve these challenges, power, water, oxygen, shelter, and food, and do it without depending on Earth, we've achieved something incredible. We've taken the first real step toward becoming a multi-planetary species. The goal is 1 million people living on Mars in a fully self-sustaining civilization. A city where children are born and grow up never seeing Earth except in pictures. Where new industries develop, new technologies are invented, and culture evolves in unique ways shaped by the Martian environment. And here's why it matters. Humanity's survival might depend on it. Earth is beautiful and precious, but fragile. Asteroid impacts, supervolcano eruptions, nuclear war, climate disasters, pandemics, countless threats could endanger life on Earth. But if we have a thriving civilization on Mars, humanity continues. Even if something catastrophic happens to Earth, our species survives. Our knowledge, culture, and achievements live on. That's what multi-planetary means. No single disaster can wipe us out. We have a backup, a second home, an insurance policy for our species. The timeline is ambitious. The challenges are enormous. The risks are real. But for the first time in human history, this isn't just a dream. The rockets are being built. The technology is being developed. The robots are being programmed. The plans are being drawn. Mars is waiting. And in 2050, if everything goes according to plan, there will be lights glowing in the Martian darkness. Lights from humanity's second home.